Okay, so this is the question where we start to talk about non-constant acceleration, and it's the question I introduced in class, where an aircraft is starting from stationary on the runway and has to reach a required speed in a distance s. So you have to work out how, given a certain thrust, and to start with, you assume that there's a constant thrust. And you don't take into account aerodynamic drag, so you assume to start with there's just a constant thrust. So given this acceleration, this starting velocity, this final velocity, what distance is required? Now, of course, that's application of the Suvat equation, and nothing more than that. So for part A, A is equal to A naught, i.e. no drag, so it's constant. And so you use v squared equals u squared, or v naught squared plus 2as. Rearrange it to make s the subject. Put the numbers in, and you get your runway distance. Now, a quick way to go from kilometers an hour into meters per second is to divide by 3.6. So you can see that you times by 1,000 to go from kilometers to meters, and you divide by 3,600. So number of seconds in an hour, but if you just divide by 3.6, you take both of those into account, and the answer is just less than 70 meters per second. So that's where this comes from, 2 times the 2 meters per second acceleration, and this is the runway distance. Okay, so for part B, you now have this drag component, so you have this functional form of acceleration dependent on velocity v, minus kv squared, where k is given, and you have to change acceleration as the aircraft is speeding up. So really the equation you need to use here is one of the three key equations. It's the one you get by combining the two root ones, so you get a times ds is equal to v times dv. And you know that this is the one you want because time is not required in this question. So once you've decided that this is the equation you're going to use, and you should always think of this if you've got a non-constant acceleration, then you can just simply start to substitute in the functional form of acceleration. So you can make ds the subject. You're looking for distance, so you're going to integrate on the left hand side between 0 and s, ds, and on the right hand side you have v dv divided by a, and then you substitute in your form of acceleration, which is a constant a0 minus k, a constant, times v squared. Now at this point you're probably thinking this is quite a complex integral, and you'd be right. You don't need to work out this integral. Anything like this in an exam, or indeed in theory, you would just be able to either solve it numerically or to solve it using a lookup table for an integral. So that's no different here. You go to the top of the question, you can see that for a certain integral where you've got x over a constant minus x squared, then there's a standard result. So making use of that identity, we can solve that to say that s, so that's the integral of this side, is equal to minus 1 over 2k times the natural logarithm of the form of the acceleration between v and v naught, or u. And then, as you know, when you have one natural logarithm minus another, you can put one on top of the other. So this is what we have here. So zoom in. So you have a naught minus kv squared over a naught. This is v naught is 0, so this becomes 0. And you can start to put your numbers in. So 2 times 4 times 10 to the minus 5 is k. K appears here, a naught appears here, and we again take our required final velocity. And this time, you solve all of that, and you find the runway distance to be 1,268. Now, should that be longer if you consider aerodynamic drag? Then if you don't consider aerodynamic drag, you have to ask yourself, use a bit of logic, then of course the answer is yes, it should be. If you're taking into account of aerodynamic drag, your aircraft is going to take longer to reach a certain speed.